Welcome students. This is our second lecture from the condensed matter physics series. We are start the superconductivity lecture. In previous lecture we discuss about the introductory portion of superconductivity. In that, the definition of superconductivity we studied in previous lectures. Similarly, the properties of superconductivity and application we are done in previous lecture. So today we are discussing about the one of the important topic from the superconductivity. The name of that topic is the Meissner effect. The effect was introduced in the 1933 by the Meissner and the Orchenfeld. These two great scientists are introduced the such kinds of important Meissner effect. The effect we are study with the help of these two diagram. Look at the diagram, this one and this one. Now let us consider the blue ball, the blue color ball, this blue color ball, it is one kind of the superconducting specimen. The lines, these lines, it is shows the magnetic field. These lines which is shows the magnetic field. Now when the superconducting specimen having the temperature is greater than the critical temperature, or it is called as the transition temperature, when the specimen having the temperature is greater than the transition temperature, the specimen which is held or which is kept under the magnetic field, the specimen which is held or kept in a magnetic field, the magnetic lines or magnetic lines or the magnetic flux are passed through these specimen. The magnetic flux is expelled from the specimen. That means in that specimen the magnetic flux are passed, magnetic lines are passed. Now in the second one diagram, the that's called as the superconducting specimen. We are going to reduce the temperature of these specimen, or we are goes to cooling of that specimen. We are going to cool that specimen below the transition current. Now in that the magnetic lines or magnetic flux are not be penetrating or not be passing through these superconducting specimen, and such kinds of effect is called as the Meissner's effect. Such kinds of the effect is called as the Meissner effect. Now let us see the statement. Now let us see the statement. The statement is shows that, or statement is told you, when the weak magnetic field is applied to a superconducting specimen, when a weak magnetic field is applied to a superconducting specimen at below the transition temperature, at below the transition temperature, that means the specimen is work like the superconductor. That means the specimen is worked like the superconducting. Now the magnetic flux is expelled. That means the magnetic lines are not passing through the specimen. That means the magnetic flux are not penetrate to this specimen, and this specimen is completely act like the perfect diamagnetic. The specimen is act like the perfect diamagnetic, and such effect is called as the Meissner effect. Such effect is called as the Meissner effect. Now just see the mathematical and such physical explanations of these Meissner effect. Now, now we are going to raise the temperature. Now we are going to raise the temperature. That means the critical temperature. That means the critical temperature or transition temperature is equal to normal temperature. The critical temperature is equal to the normal temperature. What happens when the T is equal to Tc? What happens when at that time the flux, that means the magnetic flux, are the suddenly starts to penetrate to this specimen. Look like this diagram. When we are going to raise the temperature, that means we are going to increase the temperature of specimen. That means we are goes to remove the superconducting state. In that situation, the magnetic lines or the flux which are suddenly penetrate to that specimen, and our specimen get back in the normal state. Our specimen get in the normal state. Now under this condition, the magnetic induction inside the specimen, magnetic induction in that the specimen is B is equal to mu 0 H plus M. This is the vector. This is the vector. Now what is the B? B is the simply, that is here, B is the magnetic flux density. B is the magnetic flux density. Vector M, it is the magnetization produced in the inside the specimen. The how much magnetization are produced in that specimen, which is denoted by the vector M. And what is the H? H is the external magnetic field which is by apply, which is by you apply. Now in that situation, when the specimen is in a superconducting state, in that state the B is equal to 0. In that superconducting state, the B is equal to 0. That means in a Meissner effect. That means is in a Meissner effect, B is equal to 0. B is equal to 0. And and without superconducting, that means when the T is equal to Tc, at that condition B is not equal to 0. In a Meissner effect, B is equal to 0. And what happens related with this equation? 0 is equal to mu 0 vector H plus vector M, and this equation we easily can be write, that is H is equal to minus m. H is equal to minus m, the simply equations. Okay, now the one of the important point was here, when the simple definition, if we consider, that is the superconducting material, or when the any kind of specimen under the superconductivity state, that time resistivity is equal to 0. At that time resistivity is equal to 0. That means rho is equal to 0. That means rho is equal to 0. And the current passing through that is infinite, sorry, it is a finite current which is passing through that, the fine current which is passing through these specimen. Okay, and we know from the Ohm's law, that is E is equal to I into rho, and is here the value of E is nothing but the 0. E must be 0 was here. So from another one equations which is comes from the Maxwell equation, that is del cross E is equal to minus dB, sorry I can I write here minus dB by dt, minus dB by dt. And we know under the superconducting condition, under the superconducting condition, B, what is the value of B is equal to 0. That means dB by, just a moment, okay, that means dB by dt is equal to 0. dB by dt is equal to 0, and we write already is here, that is E is equal to 0. That is E is equal to 0. That means our B is equal to constant. Our B is equal to constant. Our B is equal to constant. And this equation simply says you the magnetic flux of a line which is passing through the specimen should not change on cooling to the transition temperature. What I say once again, I just explain again. When the B is equal to 0, that means when the B is equal to constant, that means the magnetic flux of line through the specimen should not change on cooling to the transition temperature. That means when the Meissner effect are contradict this result. What I say, hence the Meissner effect contradicts these results. According to this effect, the diamagnetism is an essential property. Once again, I just say you, it is a very important sentence. Please note down. Hence, the Meissner effect contradict these results. According to that effect, which effect? Meissner effect, diamagnetism is an essential property. That means when the superconducting specimen is under the Meissner effect, at that time the resistivity is the 0. Resistivity is the 0. I can write here 0 resistivity. 0 resistivity is equal to 0, and the B is equal to 0. This is related with the Meissner effect. I just repeat the statement once again. The statement is a simple: when a weak magnetic field is applied, when a weak magnetic field is applied to a superconducting specimen at temperature below the transition temperature Tc, the magnetic flux is expelled. Now look at this diagram. Now look at this diagram. When the temperature is below the transition temperature, the magnetic flux is expelled, and this specimen is act like a perfect diamagnetic, and such phenomenon or such effect is called as a Meissner effect. And after that we see the such equations. Equation number 1, equation sorry, I can right here, equation number 2, equation number 3. Okay, just one point is remaining here. Okay, now the one point, it is related with the magnetic susceptibility. One point which is related with the magnetic susceptibility, I can write here, that is magnetic susceptibility. Magnetic susceptibility. What is the magnetic susceptibility? The magnetic susceptibility, it is the ratio of magnetization which is produced in that specimen to the external applied magnetic field, that is X is equal to M divided by H. And what is the value of H? What is the value of H? Yes, we are already done it. That is minus M. That means M divided by minus M, and this is nothing but the minus 1. This is nothing but the minus 1. This is the important result which is shows that the resistivity, it is a 0. Now students, it is all about the second lectures regarding with the Meissner's effect, and I hope you got it, the easy law from our syllabus, that is called as the Meissner effect. I hope you can enjoy these lectures, and once again, if you have any query related with this effect, then please ask me clearly. Don't be hesitant, and clearly ask and clear your doubts. I hope you can easily understood such lectures. So guys, this PDF I will send on your WhatsApp group, and thank you so much for attending this lecture. Okay.